All right, let's get going. So before we get started about probability with continuous random variables, is anyone still having trouble? You know, they're supposed to be registered, but they haven't gotten like some sort of statement from the registrar saying that they're registered? Yes? No? Kind of? Is everybody able to get on the website? No issues with that? Okay, good. The homework is due before we start class on Thursday. If you have questions, you can ask about those on Piazza. Make sure to mark your question for instructors only so you don't give away any hints to other people who are, you know, trying to plow their way through the questions. Was there any more questions about our markdown or anything like that that was talked about on Monday? No? So just make sure you upload your R markdown file and the file that it knits to by Thursday afternoon. Okay, so today we're going to start talking about probability with continuous random variables. And what if we get through all the stuff we have for today, we'll finally be in a position where we can start to use Bayes' rule for real, sort of, or at least, you know, take more steps in that direction. The stuff that we've done so far with probability, a lot of people find challenging, particularly if they haven't had a class on that before, which a lot of QMSS students have not. But, you know, don't make it to be harder than it is. Everything that we've done the previous couple of weeks with like bowling and all this really just boils down to addition, subtraction, multiplication, and division. And it's just up to you to figure out, you know, what arithmetic operations get combined with what other, you know, what x and theta and probability of this and that get combined together. So where to put what when doing, you know, it's not even really algebra, barely. It's really just arithmetic. And all of you I know can do arithmetic, even though we have, you know, considerably fewer number of people now than what we started with. But even the people who dropped, they can do arithmetic. It's just figuring out, you know, what goes where. When we start to get into probability with continuous random variables, it does involve what I would consider to be light calculus. So that is, you know, not something for like everybody in the US population to be doing, but still, you know, almost all of you have had a course on calculus before. It has not changed one bit since whenever you took it. So I think it ought to be a manageable situation, and then we can get going after we say that I'm an employee of Columbia. Columbia developed Stan. I use Stan. If I'm lucky, I might earn an extra $5,000 per year, and you should know that when taking a class like this. Okay, so we talked about the probability of X, like in the, you know, bowling context. In general, the probability that a discrete random variable takes on any value little x can depend on parameters, which I'll generically denote with the Greek letter theta. And I'll put it in boldface because in general, it might be not just one parameter, as in the Poisson distribution or the binomial distribution. It has n and pi. But anyway, if you just think of all the parameters that a probability mass function depends on and concatenate them into theta, that's how I will write this generically. And this probability mass function, you know, the numbers that come out of it differ depending on what value of theta that you are conditioning on. But X has some probability mass function that is dispersed over a discrete sample space omega, and the probability mass function adds up to 1 over the entire sample space omega. So that's what a probability mass function is. And we can define a cumulative mass function, or a CMF, as the function that yields the probability that a discrete random variable, capital X, is less than or equal to any value little x given the parameters of the distribution. And because the elements of the sample space are disjoint, we can use the general addition rule to come up with the cumulative mass function by just summing the probability mass function from whatever is the smallest element of omega to x, where x could be anything that we are interested in from the sample space. So we just add up the probability mass function from like 0 to 7, and that gives us the probability, cumulative probability, that x is less than or equal to 7. So that ought to be pretty straightforward. Sometimes we can make, you know, some simplifications to calculate this correctly, but without, you know, explicitly summing through all that. So in the case of bowling, you can do some simplification to find that the cumulative mass function of knocking down at least or at most little x pins, so less than or equal to x, is equal to the ratio -1 plus the Fibonacci number of x plus 2 divided by the quantity -1 plus the Fibonacci number at n plus 2. So implicitly, this depends on n. And that is the cumulative mass function. And if you source this in from the first week to define the Fibonacci function, then we can define our cumulative mass function for bowling, which is just this ratio here. And when we evaluate it, we see that you know, the probability of getting less than or equal to 10 pins is 1 for the first roll of a frame of bowling. Lesser values, you know, less than or equal to 6.142. Everybody understand that? Should be pretty straightforward extension of what we did before. So if you just take all these numbers here and plot them in the form of a bar chart and give them different colors. So this is the cumulative mass function, the probability of knocking down at most x pins for any number of pins along here from the sample space omega in the first roll of a frame of bowling. So these are just bar plots of the numbers on the previous one. Obviously, the probability you're less than or equal to 10 is going to be 1. And, you know, you can see the same thing for all the other numbers. So what is important on this is that the difference between two evaluations of the cumulative mass function for adjacent categories. So, you know, the difference between the dark blue one here and the purple one there corresponding to 9 and 8. So this size of this bar minus the size of this bar is the probability mass function, the probability that you get exactly 9. And that is because the cumulative mass function is defined as the probability that you get less than or equal to 9. And if you subtract away the probability that you get less than or equal to 8, that only leaves the probability that you're exactly equal to 9. So the probability mass function can be seen as the change from one step to the next in the cumulative mass function. Again, yes?
Can you explain either how this does or doesn't relate to like the marginal probability, that if you summed the marginal probability, it would equal 1, right? If you sum all the way across, like, done the marginal probability down the column and then you sum across the row, wouldn't that also be equal to 1?
Yes, if you take the joint probability mass function and sum both ways,
Yes.
then yes, equal to 1.
And that is different from this.
Right. So if you take the probability mass function and you add it all up, that's going to be 1. What the cumulative mass function tells you is that for any value of little x, what's the probability your random variable is less than or equal to that? So if you take x to be the biggest number, then it's going to be 1. You have to be less than or equal to 10 in bowling. But if you put in x equal to 5, this is the probability that you get less than or equal to 5 pins knocked down. That's only 0.086. So the probability of 0 or 1 or 2 or 3 or 4 or 5 is 0.086. And consequently, if you look at a bar plot for the cumulative mass function, the step ups are the values of the probability mass function that you're exactly equal to 9. It's, 0.6 minus 0.4 or so, about 0.2. Is there a question in the back or the front? No. Okay. All right, let's do some practice. What would be an expression for the probability that a discrete random variable x is simultaneously greater than a and less than or equal to a value little x? What would be a mathematical expression for that probability? So the probability that you get between or more than 4 but less than or equal to 7 pins knocked down in the first roll of a frame of bowling. Christina. Yes. And how did you arrive at that?
The whole thing minus the whole thing.
Right. So it's kind of just a generalization of what we said before, where there's not necessarily a gap of just 1 between a and x. Could be anything. Maybe a more formal way to write that down would be to recognize the probability that x is greater than a and less than or equal to little x is 1 minus the probability that it is less than or equal to a, or that x is greater than little x. And we can take this or apply the general addition rule to that. So we have the probability that you're less than or equal to a plus 1 minus the probability that you're less than or equal to x. That gives you the probability that you're greater than x. And if a is less than x, then there's no possibility that you can be less than a and greater than x simultaneously. So we have a 0 there. The 1s cancel, move some stuff around. We get the probability mass, cumulative mass function evaluated at x minus the cumulative mass function evaluated at a in order to get the probability that you're in the middle, which is what Christina said. All right. But in the case that x is equal to a plus 1, we can, evaluate that, and which is basically the rise in the graph here, divide by the run, plug in some things there. The denominator cancels out to 1, and the numerator, we just have the difference between adjacent categories. And so that, we said before, is the probability mass function, but it is also the slope of the line connecting adjacent categories, because you're only running by 1. So whatever you rise is the slope. So, here to there is a shallower slope than here to there, and etc. But if you're running by 1, then the amount by which you rise is the slope of a line segment connecting the tops of the bars of the cumulative mass function. Yes, Rashika.
in the fraction, but that into the cube.
Oh, right. So we have probability of something being less than or equal. That's one thing. The slope of the line is equal to the probability mass function that you're exactly equal to that one thing. Okay, so moving on to the case where we have a continuous random variable. Now our sample space omega is going to be an interval rather than a finite and discrete set. So it could be all real numbers, all positive real numbers, interval that's bounded on both sides, that can be open or closed to include the endpoints, a lot of different things that omega could be. But if omega is any interval, it's going to have an infinite number of points inside that interval. And so if you start to try to think about the probability that a random variable x could be any one point on that interval, you know, if you just think about maybe every point on that interval having an equal amount of probability, well, if it's the probability it just be one point and there's an infinite number of alternatives that it could be, you get a probability expression that is, you know, something on the order of 1 over infinity, which is just going to be 0 no matter which value of little x you used. And so that's not really going to get us very far, but you always have to keep in mind with a continuous random variable, the probability of it being any single point is basically defined as 0. So how are we going to go from there? Well, we can still think about the probability that a continuous random variable x could be less than or equal to some number little x from omega, and that function is going to be, you know, greater than or equal to 0, in general, greater than. And so that's a non-vacuous function or expression that we could think about, and it has a name called the cumulative density function or the cumulative distribution function. You'll sometimes see it both ways. Either way, abbreviated CDF. And there's really no conceptual difference between a cumulative mass function, cumulative density function, cumulative distribution function, except to emphasize whether your sample space is discrete or a continuous interval, which you should always be keeping in mind anyway. So people can be a little bit sloppy about distinguishing between these two things, but it's not that big a deal. And in fact, you know, for most of this class and this semester, I'll use the same symbol, big F, to refer to either the cumulative mass function or the cumulative density function of x. And hopefully it'll be apparent from the context whether we're talking about discrete random variable or continuous random variable. But either way, we're using big F to represent the probability that, you know, the random variable that we're talking about, whether it's discrete or continuous, is less than or equal to whatever little x we put into this function. And so here is an example of a cumulative density function. It's defined for all real numbers, even though I chop it off at -4 and 4. Since it's a function from omega to the 0 to 1 interval, it's bounded by 0 over here, bounded by 1 over there. Cumulative density functions often have this kind of S shape to them. They have to get, you know, flat eventually on the endpoints in order to stay between 0 and 1 and consequently be admissible for the probability that you're less than or equal to, you know, something. So as we can see on this continuous interval, we've got our CDF curve here, and we can see that the slope of the CDF is also changing, you know, as we go from smaller values of x to bigger values of x. That will be important. We can also see that the cumulative density function has to be an increasing function. So if the probability that you're less than or equal to, you know, 1 is whatever, the probability that you're less than or equal to 2 has to be bigger than that. So cumulative density functions are always strictly increasing functions. Questions about what a CDF is? Okay. So this previous CDF here is actually a particular CDF. It's the CDF of what's known as the standard logistic distribution over the real line. And it has a particularly simple cumulative density function, F, which is defined as 1 divided by the quantity, 1 plus E raised to the power negative X. It's about the simplest one we can do over an infinite interval. And then we might ask ourselves a question, or I might ask you a question. What is the slope of this cumulative density function at the value little x? Partial derivative of that with respect to x, the random variable that we are talking about. So what is the partial derivative of this particular CDF? No. Merlin.
We have two functions here. One over u, and we have u with 1 plus power minus x. We take the function times the derivative of the bottom, which is e to the power minus x. That's how
E works, yeah.
Times plus bottom one times the derivative of 1 over minus by u, which is minus 1, because it's u to the power minus 1, then minus 1 minus e to the power minus.
Maybe. So, just using the rules that you may have not used in a few years, to take the derivative of the CDF, in the bottom here, this is implicitly raised to the power negative 1. And so we've got a squaring in the denominator and a negative 1 in the numerator here. And we need to multiply using the chain rule by the derivative of e to the negative x. E is a special function. It's its own derivative. So we have an e to the negative x in the numerator here. And then we need to use the chain rule to multiply by the derivative of negative x with respect to x, which is negative 1. Cancels out this negative sign over here. And we are left with e raised to the power negative x divided by 1 plus e to the negative x quantity squared, which is going to be a positive number. So because the CDF is an increasing function, the slope is always going to be positive. So if you do something and you find out the slope is negative, you've done it wrong. Need to go back, do it right. Now, these days, you don't even really have to know what you're doing, because you can just go on the internet and type in, I don't want to differentiate that function, but basically all you have to do is type 1 plus, and know that Mathematica has this kind of weird convention where they use capital letters for functions and brackets for function calls. Then you click on this little equal sign, and it comes back with what we just said. So you don't really have to memorize all the rules of derivatives that you memorized at one point. You just have to memorize like where the lecture notes are and then click on this link. You'll go to Wolfram Alpha. There's other websites that'll do derivatives for you, but it's basically something that's very simple to program into a computer and has been done, you know, all over the place. So as long as you're okay with like partial derivative is a slope, you can figure out what the function representing the slope is if and when you need to. But, you know, the vast majority of them have, or not the vast majority of them, there's an infinite number of them, but the ones in common use, they've already been figured out. And so the derivative of the CDF for a continuous random variable is called the probability density function, or PDF, and is denoted by me with little f of x. Again, it can depend on parameters, although this one doesn't. It's always going to be positive. You will see other people, like the textbook and stuff, use p here rather than f. That's just a convention. But I like to use f to try to emphasize to you that the probability density function is not a probability. It is the slope of the CDF. The CDF returns the probability random variable x is less than or equal to little x, but the slope of a CDF is not a probability. It's just a slope. Nevertheless, the probability density function for a lot of purposes is used the same way we use a probability mass function in the case of a discrete random variable x, and the probability mass function actually does return a probability that x is exactly equal to little x, but that only makes sense when the sample space is discrete. When the sample space is continuous, the CDF, very simple, not complicated, makes sense. CDF has a slope, that makes sense. You can figure out what the slope is by having Wolfram Alpha differentiate the thing. So we'll say that makes sense. And then if you just remember that the PDF is a slope, then hopefully you won't get confused. But the sure way to get confused is, and admittedly having a name like probability density function is perhaps confusing for something that is not itself a probability. But as long as you keep that in mind, you ought to be okay. So just like in the case of a discrete random variable, we can define the probability that x is bigger than a and less than or equal to x as the difference in the CDF evaluated at x and a respectively. So that's the same in the continuous case as in the discrete case. If we let x be a plus h and we calculate the rise over run ratio, sticking in a plus h for x here, the denominator leaves you h. That is going to be the slope of a line segment connecting a and a plus h with the heights evaluated at their respective CDF values. And then if you let h approach 0 from above, you may recognize this as the definition of a partial derivative of the function big F with respect to x. And so it's going to be the rate of change in the CDF at x, or the slope at x. And so whether we're talking about discrete or continuous random variables, we can always think about the rate of change as being equal to the other function. In the case where the sample space is continuous, this is the instantaneous rate of change in the CDF at x. If the sample space were discrete, then this is the sort of step change in the cumulative mass function at the margin. But it's still the same concept, really. You just have to make an allowance for what sort of sample space your random variable is being defined on. But it's still the rate of change. Questions about that? Yes?
So it's kind of like you.
And that's what it's kind of about. Okay. If we don't get to it today, post on Piazza. Okay, so that was the logistic CDF. It is about the easiest one we could do. It's not the most common. Most common is the standard normal CDF, also defined over a sample space that includes the entire real number line. And the standard normal CDF is so fundamental that it has its own Greek letter. And since Christina jumped in earlier, leave it up to the rest of you. What is that ancient Greek letter? Yeah. In this country, we tend to say phi. But who knows which one it's really, right? Anyway, it's defined as 1/2 plus the product of these two functions, little phi, phi, whatever, evaluated at x, which is this function here, multiplied by s of x, which is this function here involving an infinite summation. Now, these CDFs, although conceptually simple, often are impossible to write down in a closed form. And even when it is possible, they tend to be ugly. You should actually consider yourself fortunate that this merely involves infinite sum, although it does involve the infinite sum of a so-called double factorial, which you may not be so familiar with. But it's basically like the factorial function, except you step down in steps of 2 rather than in steps of 1. Not a hugely important thing to remember, but anyway, it's a factorial where you step down steps of 2. Anyway, so if this is the CDF, the probability that x is less than or equal to little x, what would be the slope of the CDF? That would be the PDF. This one, not too hard, but more complicated than the one we did previously. Derivative of 1/2 is obviously 0. Don't need to worry about that. The derivative of a product is equal to the first one times the derivative of the second plus the derivative of the first multiplied by the second. So we got little phi here multiplied by the derivative of s. This involves the exponent here, raised to the power 2n plus 1. So you bring that down, subtract 1 off the exponent here, and you get this. And then we're subtracting the derivative of little phi, which is this. It involves e. So when we take the derivative, it's going to be all this. And then there's a chain rule thing where we have x squared divided by or multiplied by negative 1/2. Bring down the 2. This comes out to be negative 1. So negative phi multiplied by x multiplied by s. Factor out the little phi. And we get a combined statement here where these all involve even powers of n. And if you evaluate this at n equals 0, n equal 1, n equal 2, you get something like this. And you can see basically everything cancels out, but the 1 leaving yourself with little phi of x, that being the slope of big phi. So little phi is the standard normal PDF. And it is this function right here. So actually going from the CDF to the PDF doing the differentiation, you could have asked Wolfram alpha for this, but maybe it's worthwhile to just kind of go through 1 or 2 of these to see how they were done. Obviously, you can look up the formula for standard normal PDF, and it produces the red curve here. This is kind of a stretched out picture, but this ought to be the familiar bell curve type shape that you associate with the normal distribution. Now, maybe you didn't know it, but this bell curve thing is actually the curve of the standard normal PDF. It's just as conceptually valid to look at the standard normal CDF, which is the black line here. And the CDF is honestly easier to understand, even though you see the PDF more common, and it's more common that we would make use of that. We'll come back to the green one in a second, but just looking at the black and the red, these functions here, we can answer some questions like, what is the median of the standard normal distribution? Okay. Louder. 0. And how did you come up with that? Yes. So in the case of a continuous random variable, the median is defined as the value from the sample space such that exactly 0.5 of the cumulative density is to the left and exactly 0.5 is to the right. So you could start at 0.5, go over to the black curve, go down to the horizontal axis, and you get 0 in the case of a standard normal distribution. What then would be the mode of the standard normal distribution? And how did you know that? Correct. So in the case of a continuous random variable, we define the mode as the value of the PDF that is where it's at its highest over the entire sample space, or you can equivalently think about that as the point on the CDF where the slope is the biggest. Same concept. Okay, so that's how we define mode and median in the case of a continuous random variable. Those are both 0 in the case of a standard normal distribution, which is to say they are the same number. Nevertheless, the median and the mode are always different concepts, even if they happen to be the same number in the case for a symmetric distribution like the standard normal. Moving on, how do we calculate the expectation of a function of a continuous random variable defined for some interval omega? So we said before that the probability density function is not a probability. But if you want to get, not too technical, but like hand-wavy technical about the probability that a random variable x falls in some small interval defined as x as the left endpoint and x plus dx as the right endpoint, probability x falls in that small interval is going to be the PDF little x multiplied by dx. So basically forming just a little very slim rectangle there that has height little f and width dx. And dx is this infinitesimal number that you can think about as basically the smallest piece of x that is non-negligible. So if we had like dx times dx, that would be so small that you didn't even have to worry about it. But dx is sort of like the smallest piece of a random variable such as x that you still have to worry about. But it's basically a number that is like arbitrarily close to 0. And so if you think of little f times dx as the probability that random variable falls in this little interval, then we can define the expectation of some function g, provided it exists, as basically a very similar formula to what we did before in the case of the function of a discrete random variable, except now we're not summing, or we're not using summation, we're using integration over the entire sample space of the function that we're interested in, multiplied by the PDF, multiplied by dx, integrated over all of omega. And if you can work out that integral explicitly, you're going to get a new function, the so-called indefinite integral. And to get the definite integral, which is what we're interested in the case when we're doing expectations, you can take your indefinite integral function, evaluate it at the biggest value of the sample space, subtract the value of the indefinite integral evaluated at the smallest value of the sample space, and that difference is the definite integral, or the amount of area underneath the curve. And since the PDF can depend on parameters theta, this indefinite integral is a function of parameters theta, etc. But when you evaluated the biggest value, you evaluated the smallest value, subtracted out, it's no longer a function of x anymore once you put in those particular values of x. Now, one thing you have to worry about is this integral may not converge. In that case, we say the expectation of g is not defined, but if it is equal to this quantity. And actually working out what an integral is much more difficult for a computer than a derivative. A derivative is really just a sequence of rules that we can program into a computer, but there's no like comprehensive way of doing integrals. It's basically just a bag of tricks, and you can teach the computer all the tricks, but the tricks are only sufficient to cover a very small number of functions that we want to do integration of. And so most integrals are actually impossible to write down in any sort of a closed form. We'll learn how to do simulations to approximate those arbitrarily well, so don't sweat that too much. You just basically need to understand integrals conceptually, or definite integrals are area under the curve. And integration is like the inverse operation of differentiation. You can take like a CDF, differentiate it to get the PDF. That's the slope. You can take the PDF, which is a function that gives you the slope, integrate it, and you're back to the CDF, the amount of area to the left of a point in the PDF. Now, for integrals that are possible to do, you can click on this link. No. Went to the wrong damn website. You can type in definite integral, and then the function that you want to integrate, the variable, the limits, hit enter. If it's possible to do, then a website like this probably will give you an answer, but most are not really possible to do in any sort of an explicit form. So some examples of expectations of functions of continuous random variables that we're interested in, these g functions that we might want to use to calculate their expectation, this is the same g functions that we were using in the case of a discrete random variable. So if g of x is just equal to x, then expectation of this is just the expectation of a continuous random variable denoted mu. If we take the function x minus mu quantity squared, find the expectation of that, that's just going to be the variance, etc. So same g functions. We're now using integration rather than summation. And integration is basically adding area, whereas summation is adding points. But that's just what you need to do to move from discrete random variables to continuous random variables. So what I put on this, the green curve here, is the function g of x is equal to x multiplied by the PDF of the standard normal distribution. That's denoted d norm in R. And I get this green line here, which is sort of the mirror image across y = 0 here. And so if you sort of take the amount of area over here to the right, as positive area, and then the area over here to the left of 0 as negative area, add those two chunks of area together, looks like you're going to get 0. And in fact, the expectation of the standard normal distribution is 0, and that can be seen by remembering that the standard normal PDF only involves x squared. X doesn't come in, linearly or anything like that. So if we take our integral from negative infinity to infinity, split it up at 0, which is totally a legal thing to do. If we put in, some value negative x, well, this one is going to have a negative sign, but phi is going to be the same. And so this over here is going to have the same magnitude as that over there. Provided that both of these converge, they're going to offset each other. So the expectation of the standard normal distribution is 0. Salif.
We understand why this fitting where it's
so I chose 0 in order to make the point that this offsets exactly with that. You can actually, if you have any integral from like a to c, you can decompose that as the integral from a to b plus the integral from b to c. It's really just the idea of addition being associative but applied to area rather than points.
This means like you could basically choose
Yeah. So I'm saying the area for the whole green curve is equal to the area up to 0, which is negative, plus the area from 0 over to infinity, which is positive, but they're equal in magnitude, and so they offset.
this from the formula. I know the slide before. The G, yes, this one. Right side. Yeah, that part.
Yeah.
Because the maximum of the sentence is
Positive infinity. And the minimum, negative infinity. So if this had been defined on some subinterval of the real numbers, it would only do the integration over that integral. Now, to figure out the variance of a standard normal distribution, it's a little bit harder. We have to use substitution. So let's define a new variable y, which is x squared over 2. If we differentiate y with respect to x, it's just going to be x. So dy dx is equal to x. We move the dx over here. We now have dy is equal to x times dx. And so if we go to calculate the variance, since the mean is 0, x minus 0 is just, or x minus 0 quantity squared is just x squared times the PDF of the standard normal distribution multiplied by dx. So if we insert the explicit form of the PDF, take one of the x's, move it over here. Now we have x dx, and we're ready to substitute in terms of y and do the integral over y instead of x. So we take x dx, make that into dy. We have negative x squared over 2. That's what e is raised to the power. So now e is raised to the power negative y. And then we have one more x here, which is equal to the square root of 2y. So we've substituted y's for x. We pulled out the 1 over square root of 2 pi. And also we noted that if you integrate from negative infinity to infinity, in the case of a symmetric distribution, that's equal to integrating from 0 to infinity and then multiplying by 2. So we've got all that out front. We have this expression here, which simplifies to something of this form. Y raised to some power times e raised to the power negative y multiplied by the change in y integrated from 0 to infinity. That is a special mathematical function that happens to have its own Greek letter. This is capital gamma, not to be confused with the lowercase gamma that we were talking about last week, and not to be confused because the implementation of it in R actually uses the lowercase g for this, and it uses the capital G for something else. So anyway, lots of opportunities to be confused, but this refers to a special mathematical function that's defined as this integral. And the gamma function is basically a continuous generalization of the factorial function defined for non-negative integers. And in some cases like this one, we can evaluate it exactly. So gamma to the 3/2 is equal to the square root of pi over 2. That all cancels and it leaves 1 as being the variance of the standard normal distribution. But even when we can't evaluate it exactly in closed form, R is able to produce like 16 digits of accuracy for this integral if you just type in gamma z in R. So basically the deal with integrals, anytime you have an important integral, especially an important integral that only involves one variable, if it's important, somebody has figured out a good way to implement it on a computer. What's a little bit or a lot difficult is doing arbitrary integrals, particularly arbitrary integrals in multiple dimensions, because that's not like a well-defined enough problem for someone to sit down and implement a good way to evaluate that integral numerically. We often have to do it with simulation or whatever. But basically, any one-dimensional integral, as long as the function is not too crazy, we can just ask a computer to integrate for us with like little triangles or little trapezoids, and just like add them up. A little bit of adaptation, but basically it's a not hard problem for a computer. But this is a particular integral that is special enough to have its own Greek letter and its own implementation in R, and like every other language, probably including Microsoft Excel, is going to have a function to evaluate this. But it's just defined as this integral. It's not anything that we can do to get the indefinite integral of this in any sort of a useful form. All right, so standard normal distribution has an expectation of 0, a variance of 1. Anytime you see standard out front of the name of a distribution, it basically means for the easiest parameter values to work with. It doesn't really have a well-defined meaning. But notice what we did here to get the variance. We solved this integral by doing substitution, and we had to do, work with the differentials here in order to do the change of variables in that substitution in order to solve this particular integral. Not that you necessarily need to memorize how to do integration by substitution anymore, but it's a concept that comes up when we do transformations of continuous random variables. So I've been teaching this Bayesian class for like 5 years now. And every year we talk about, transformations, particularly shift and scale, stuff like this. And it's not that difficult. And yet every year you people manage to screw it up completely. Like you screw it up in class, you screw it up on the homework, you screw it up on the final. It doesn't really matter how many times I explain how to do this. You're still going to screw it up. So at least remember that you're prone to screwing it up and look it up in the notes again. All right. So if z is distributed standard normal and x is a function of z, namely the function mu plus sigma times z, not talking about a real complicated function here. What is the PDF of x if z is standard normal? How will we go about doing something like that? First, we need to come up with the inverse transformation of the function that we have here. So if x is a function of z, mu plus sigma z, then z as a function of x can be written as x minus mu divided by sigma. Again, that's just algebra. And not very difficult at that. And since this is a monotonic transformation that we're talking about from x to z, the CDF, probability that x is less than or equal to little x, has to be equal to the probability that the random variable z is less than or equal to z, little z, considered as a function of x. So this inverse transformation here. So in the case of a standard normal distribution, that is going to be big phi evaluated at z as a function of x. So we're actually going to be putting in x minus mu divided by sigma in there. And so that's going to be a function of x. Now, if we want the PDF of the random variable x, we need to differentiate this CDF with respect to x rather than z. Or, well, we differentiate with respect to z, but then we chain rule it. We end up with the derivative with respect to x. Okay, so we take the derivative of phi evaluated at z of x, differentiate with respect to x. We use the chain rule one time, take the derivative of phi with respect to z, multiply by the derivative of z with respect to x. CDF with respect to z is the PDF. Derivative of z with respect to x is 1 over sigma. Multiply those two things together, writing out our PDF in terms of x rather than z. We get 1 divided by sigma divided by square root of 2 pi times e raised to the power of negative 1/2 multiplied by z squared, but z written in terms of x. So x minus mu divided by sigma, quantity squared. So basically, the general procedure to deal with transformations that are increasing is to take the CDF, differentiate it with respect to z, use the chain rule to get the derivative of your inverse transformation, multiply those two things together, plug in terms of x rather than z. You now have a PDF for this continuous random variable x, function of z. Zhu. Yes. So we know the distribution of z. We want to find the distribution of x. So we use our distribution of z, but we have to write it as a function of x and differentiate in order to get the PDF for x, since we already know what the PDF of z is. All right. We'll practice that like 12 times over the course of the semester. So when we do these transformations, it makes it particularly easy to figure out what the expectation, variance, etc. of x is, because we know what the expectation and variance of z are. So expectation of x, plug in the function, mu and sigma are constants, can pull them out. Expectation is a linear operator. We get mu plus sigma times the expectation of z. Expectation of z is 0, so we're left with mu. Expectation of x is mu. Expectation of x minus mu squared. So take x, subtract mu, square it. That's sigma squared, z squared, the expectation of that. Can pull out the sigma squared, multiplied by the expectation of z squared, which is 1. Consequently, the variance of x is going to be sigma squared. So I chose those variable names in this transformation on purpose. This PDF that we derived here is the PDF of a general normal distribution that has parameters, the expectation mu, and the standard deviation sigma. Sigma implicitly is positive throughout all this because it's a standard deviation. But in any event, this is the PDF of the general normal distribution that we generated from the standard normal distribution according to this transformation of a standard normal random variant. So this is how these probability distributions get made, for lack of a better word. Oftentimes we start with a simpler distribution, apply a transformation to that, and then figure out what the CDF and the PDF and so forth are of the new variable X. And so we can just proliferate to a whole lot of different probability distributions from a small set of simple error probability distributions and a bunch of relatively simple transformations thereof. Question over here. Question over there. All right. Let's do some more practice. But the normal distribution is one of several where you can do this scale and location transformation, logistic distribution, uniform distribution, that are a bunch in the location scale family, that when you do transformations of this form, it stays in the same family of distributions, but the parameters change. So standard normal is normal with an expectation of 0 and a variance of 1. General normal is defined as a transformation of that. It's still normal. It just now has a general expectation mu and a general standard deviation sigma as parameters to that distribution. So you can basically stretch out a normal distribution, shift it over left or right according to whether mu is positive or negative. It's still going to be normal in the normal family when we applied this shift and scale transformation to it. All right. So what about transformations that are monotonic but not linear, such as the case, what if Z is distributed normal, general normal, and X is defined as a function of Z, E raised to the power of Z? What is the PDF of X? And I give you a hint. Use the CDF of X, which can equivalent be written like this: X less than or equal to little x, or Z less than or equal to little z, but little z is a function of X. So how would we go about attacking this problem? Andres. Right. So what is the function? Z is a function of X. Log X. Natural log of X. Good. That's a good start. Now, how do we go from the CDF of Z to the PDF of X after noting what the inverse transformation is? Okay. How do we go from a CDF to a PDF in general? Okay, so we want to go from the CDF of Z to the PDF of X. What do we need to differentiate with respect to? X. And that's going to entail using the chain rule one time based on the derivative of the inverse transformation. Just kind of put that together. We got this. Log derivative of log of X is 1 over X. So the PDF with respect to X is the PDF of Z evaluated as a function of X, because the PDF of Z is the derivative of the CDF of Z with those parameters, multiplied chain rule style by the derivative of Z with respect to X, which is 1 over X. Put that all together, write in terms of X rather than z. So we get 1 over x, all this stuff, log x minus mu divided by sigma quantity squared. Of course, that's only going to be well-defined if x is non-negative. Otherwise, we're not going to be able to take the logarithm of it with real numbers. And so that is the PDF of the so-called log normal distribution of x over the sample space, all non-negative real numbers. And the reason why the log normal distribution has its name is because the logarithm of x has a normal distribution. So we're just doing some relatively simple transformations here and doing the corresponding relatively simple calculus to get there. One thing about the log normal distribution, it's not in the location scale family. So mu and sigma here refer to the expectation and the standard deviation of z. The expectation and standard deviation of x are not those due to the nonlinearity of the transformation that we're doing here. So if you look up on Wikipedia or whatever, you can see the expectation and the variance of x. Those integrals are doable. They just come up with slightly more complicated expressions for what the expectation of x and variance of x are. But the process that we go through to figure out the PDF of a transformed variable is going to be the same for any sort of a monotonic transformation. In general, you might have like a decreasing transformation or something like that. That would make your PDF come out negative. You know that can't be right. So in general, the correct thing to do is to multiply by the absolute value of the derivative of z with respect to x. But when this is all positive, then the absolute value doesn't matter. But the technically correct thing is to multiply by the absolute value of the derivative there so that your PDF comes out positive. Okay. Scale transformations of so-called exponential random variables. So the standard exponential distribution is defined for all non-negative real numbers. It has another extremely simple CDF, 1 minus e raised to the power negative x. So what would be the PDF of the standard exponential distribution? E to the negative x. And may have forgotten to say this earlier, the integral of a PDF is always 1. So that follows, you know, the PDF is the slope of the CDF. And so here we have the CDF. If we evaluate it at the biggest value of x and the smallest value of x, subtract that out, that's just going to be 1 minus 0, which is 1. So just like in the case of a discrete random variable, the probability mass function summed up to 1 for over the entire sample space omega. In the case of a continuous random variable defined over some interval omega, that must integrate to 1. So there's 1 unit of area that you can allocate across omega however you want, or according to the rule that defines these variables. And so the standard exponential distribution is defined by the rule. The probability that a standard exponential thing is less than or equal to some value little x, where little x is some positive number, is 1 minus e to the negative x. Differentiate that. We now have the PDF of the standard exponential distribution, which integrates to 1. So what would be the expectation of x, this standard unit exponential variant? How would we figure that out? conceptually.
Roll over the entire sample space of x, e to negative x.
Correct. And the entire sample space here is the non-negative real numbers. So Robert told us this. You type into Wolfram alpha or whatever, you can see the indefinite integral is the quantity x plus 1 times e to the negative x. If you differentiate that, you get x times e to the negative x. So you can just convince yourself of that. We need to evaluate it at the maximum and the minimum, which is infinity and 0. Here we technically get something that's improper. So this is infinity multiplied by 0. That's not well defined. But this first term is going to negative infinity at a linear rate. This second term here is going towards 0 at an exponential rate. And so if you do L'Hopital's rule, this is going to tell you the whole thing has a limit of 0. So ignore that. Plus e raised to the power of 0, which is 1. So this is going to have a limit, a well-defined limit of 1, which is the expectation of the standard exponential distribution, which is a very nice and simple distribution involving random variables that have to be positive. Okay? Everybody see how we did that? What is the variance of a standard exponential distribution? And how would we figure that out conceptually? Christina.
The integral of that of x squared minus.
Right. So we get this, we learned last time, and it's also true for continuous, that the variance of x is equal to the expectation of x squared minus the square of the expectation. Square of the expectation is just 1 in this case. So we could figure out what is the expectation of x squared, right? Or we could do it this way, just take the quantity x minus 1 squared multiplied by e to the negative x multiplied by dx, integrate that over the non-negative numbers. You get this, so you can break up an integral of a sum into these pieces. We just saw that x e to the negative x, that integral is 1. We know that e to the negative x times d of x, which is just the PDF, that integral is also 1. Is sort of a miracle of the exponential distribution that both of those integrals are the same. We're left with this one. Type it in. You can convince yourself that it's this. Evaluate it infinity at 0. Similar deal here. Get the limits of it. This is going to come out to -2 or something, or +2. Whole thing comes out +2. Those cancel out. And you get 1 again. So the variance of a standard exponential is also going to be 1. Yes? Right. So in general, this is x minus mu. And we just established that the expectation of x was 1. Right? So the general definition, the expectation of x minus mu squared. If mu is 1, then just plug in 1. Anyway, all those integrals are doable enough. So if x has a standard exponential distribution and y is defined as mu x, where mu is any positive number, what is the PDF of y? Right, so what is the inverse transformation? Correct? Where do we put that? Where do we put the inverse function? Into the CDF, and then we differentiate with respect to y. So this is that, writing y as a function of x here. So we want to take our CDF, instead of x, we put in y over mu, differentiate with that with respect to y. You get 1 over mu times e raised to the power y over mu. And oftentimes you will see this general exponential distribution written with the substitution lambda equals 1 over mu. So they just write lambda times e to the negative lambda times y. But it's really expressing the same thing. And the mean, the expectation of the standard exponential, of the general exponential distribution is mu, and the variance of a general exponential distribution is mu squared, which you can work out just by doing these transformations. Okay, we're almost out of time. Just the last slide for today, like what's the road ahead, what's for Thursday. So we usually think about parameters as being continuous, which is why it's sort of been hard to come up with realistic examples of Bayes' rule only using discrete probability theory. But now that we have mastered probability with continuous random variables, if you just sort of take Bayes' rule and you think about it as a limit, as you sort of discretize a continuous random variable into little chunks, let the number of cuts go to infinity, you get Bayes' rule for continuous random variables. The PDF of theta given data y and whatever parameters go into your prior has this expression over here on the right. A prior PDF for theta, y could be either discrete or continuous, so a PMF or a PDF for y given theta. And then we've got the denominator term here, which depends on y, but not on theta. And so if you have data, how can you go evaluating this? Well, the numerator is going to be pretty straightforward. It's just prior times likelihood. Denominator is going to be more difficult, but once you've chosen your prior and your likelihood function, in principle, you can do the integral of the numerator over theta to obtain the denominator. It's the definite integral here. This is just going to be some number because y is known, a and b are known for a prior, to complete Bayes' rule and therefore imply the left-hand side, which is the PDF for theta, which you don't know, conditional on the data, which you do know, and whatever beliefs you came into it with. So this is how we update our beliefs about a continuous theta as data come in. So that's what the reading for Thursday is going to be about for one particular case, and that's what we'll talk more about on Thursday after we go over the answers to the homework. So I'll see everybody then.